Good afternoon, everybody. Welcome to our last panel. This panel, we will have three more interesting talks. And right now, we are going to continue with FPGA realization of a MIMO OFDM radio frequency transceiver with 256 QAM modulation. You are Fernando, right?
Yeah. Hello.
Okay, so you have 1 hour for your talk. No, it's I'm kidding. Officially, we have 20 minutes, but we have time. So if you want to give details on your talk, so feel free to take some minutes more.
Okay.
Go ahead.
All right. Thank you. Well, first of all, hello. My name is Fernando, and I'll be presenting the work titled FPGA realization of a MIMO OFDM RF transceiver using 256 QAM modulation. Overall, the contents for this presentation will be a brief introduction to the technologies used in this work, mainly 256 QAM, MIMO, and MIMO, and OFDM, as well as the transceiver architecture proposed for this work, and some system generator emulations of the system working and everything, along with some conclusions and the references for this work. First, regarding 256 QAM modulation, basically this is a modulation scheme that consists of applying changes to the phase and the amplitude of the signal. This is based on in a way that allows us to obtain up to 256 points or different symbols. And to achieve this, we need an 8-bit data input, and it can be represented mathematically using equation 1. Here we can see that we have a cosine and a sine, and we have two main components. We have I and Q. I corresponds to the in-phase component of the signal and represents the real part of the signal, and Q corresponds to the quadrature component of the signal, and it corresponds to the imaginary part of what will be the signal. And this type of modulations can be represented using constellation diagrams. And here in figure 1, we have an example for QPSK modulation, which is basically a 4-symbol modulation. But we can scale this up to kind of imagine what 256 QAM will look like. Then we have orthogonal frequency division multiplexing. And this is essentially a multi-channel technique that allows us to divide the communication channel in sub-channels so that we can use different frequencies to help us mitigate timing issues when you're trying to send information. Sometimes we have a data stream that takes too little time between each data point, and our systems cannot process this information in so little time. So by dividing the channel in subchannels, we can give it a little bit more time to kind of do a parallel processing of each of these subchannels. And basically, it's called orthogonal because the frequencies that are used in this channel are orthogonal to each other. This means that, as we can see in figure 2, the peaks of the frequency of interest align themselves with the nodes of the adjacent frequencies. So whenever we're trying to measure the peak of a specific frequency, ideally we wouldn't have any type of interference with the other signal. Next, we also use multiple input, multiple output technologies, specifically the Alamanti scheme. And for this scheme, we have the block diagram in figure 3. We can see that we have 2 transmit antennas and 2 receive antennas. And essentially what we're doing is we're using the transmit sequence shown in table 1 to kind of introduce redundancy into the system so that we can later on detect errors or mistakes in the transmission of the information. Basically, at the first time period in antenna 0, we will be sending the data as 0, and in antenna 1, we will be sending the data as 1. And at the next time, we will be sending in antenna 0 the negative conjugate of S1, and in antenna 1 the conjugate of S0. So we can see that we have like the information, but in a different format, so that we can later on compare it. To decodify this sequence, we basically need a channel estimator, a combiner, and a maximum likelihood detector, as we can see it in figure 3. The proposed architecture for this work is based on the block diagram shown in figure 4. Here we have a OFDM transceiver, and essentially we start with digital modulation. In our case, it's 256 QAM. Then we divide the data stream into multiple subchannels using a series to parallel converter. And we multiply each data stream by a different oscillator. And these oscillators have frequencies that are orthogonal to each other. After that, we're going to sum up all the signals into a single one, and this will output a OFDM signal. And in the receiver stage, we will be taking this OFDM signal and once again multiplying by the original oscillators. This will help us isolate the each frequency. And by using an integral, we can kind of get the tendency of each data point on each subcarrier. And later on, we can assign a value to this tendency and concatenate all the information into a single data stream using a parallel to series converter to later on apply either a detector or digital demodulation. Or in this case, we have the implemented system in MATLAB Simulink using system generator for DSP blocks. And we can see that we have a data source. That in this case, we have a data, one data bit every 10 microseconds. And we have our modulation block. This, in this case, is 256 QAM. We have 2 transmitters and 2 receivers that aligns with the MIMO implementation. And we have the MIMO decoding blocks. We have one for each component. And later on, we have the demodulation, and we have some scopes and a few blocks to measure the bit error rate and the EBM. I would like to get into each of the blocks for the system. We have first the 256 QAM modulation. In this case, we have our input data, and we're using a series to parallel converter to separate these input data into different data streams. We later on use multiplexers to kind of assign different amplitudes and different phases to the signal, and we end up with 2 signals. We have the I component and the Q component. After that, we're going to take those components and we're going to go into the transmitters. We have 2 transmitters. This is the block diagram for one of them, specifically the antenna 01. And in this case, we're going to multiply by each of the oscillators, and we're going to be applying the Alamanti sequence using the negation with an amplifier with a value of -1. And later on, we're gonna add up all the signals into a single one. We later on will have the receiver. For in this case, the receiver for both antenna 0 and antenna 1 is the same. It's identical, and we're basically once again multiplying by the oscillators, and we're using an accumulator block to apply this integral over the period that corresponds to a single data point to get its tendency, and using a function, we can assign a value to later on concatenate all of this information into a single data stream. After that, we will be applying the MIMO decoding, which in this block, we basically have the previous functions that were shown in figure 3, those being a combiner and a maximum likelihood detector to recuperate the original data. And after that, we will be applying the modulation. Here we take all of the information from each of the data streams, and we end up with a single one. And we apply different conditions so that we can reconstruct the original 8-bit data from the values that we had. Here we have a simulation for the system. In the top signal, we have the data input in binary form, and the 2 middle signals correspond to the OFDM signals for antenna 0 and antenna 1. And after that, we have the data output that has been reconstructed. We can see that we have a little delay for when the system starts working. And this corresponds to a delay between the data input and the time it takes to start getting some information from the system. This delay was applied to all of the signals so that we can kind of compare it more easily. We also generated some graphs for both the BER and the SER of the system. The overall result that we got was that for these graphs were obtained using different modulation schemes. We also applied BPSK, QPSK, and 16QAM. And we overall got that for BPSK and QPSK, we had very, very clean signal. And by applying noise, if it was upwards of 2.5 dBms, we have less than 1% of errors. In the case for 16QAM, this happened upwards of 8 dBms. And in the case for 256 QAM, we needed at least 14 dBms to achieve this same error level. We also have the resource utilization considering an FPGA RTX7. And we can see that for the available loops of the system, we use 37.08%. We use 1.15% of the available registers, along as 8.76% of the memory modules and 32.7% of the DSP blocks. We can see also like the utilization of each of the blocks that conform the system. We can essentially see that overall, almost all the systems use less than 1% of the available resources. An exception is the receiver block, which is shown in table 5. And we can see that this is the most resource-heavy system with an utilization of the loads of 17.92% and a utilization of DSP blocks of 12.97%. This corresponds to the accumulator and the multiplications that are done in this specific block, and that is why this is the more resource-heavy system. And finally, we have some conclusions. We can see that the implementation of the RF transceiver using MIMO and OFDM technologies was successfully achieved but via system generator for DSP blocks, which is a means to apply high-level synthesis so that we can access FPGAs as a platform, even if we don't have the expertise to program in VHDL. It was also observed that for BPSK and QPSK, we had error rates below 1% after 2.5 dBms. For 16QAM, this was achieved at 8 dBms, and in the case for 256 QAM, this was achieved at 14 dBms. And this is mainly due to intersymbol interference, and due to that in QAM modulation, sometimes the symbols are too close to each other. With a little bit of noise, we could end up confusing or not detecting the symbols correctly. Overall, we can conclude that using FPGAs as a platform to develop hardware implementation of digital wireless communication systems is fully viable, and it is of great interest primarily so that we can promote the development and the evolution of these systems in a faster way. And for the case of the system as a whole, we had a data input every 10 microseconds. This resulted in a data rate of 6 megabits per second, and we had a delay of 90 microseconds between the digital input and the digital output. Overall, I think that would be all for me. Thank you for listening, and we have some of the references used for this presentation.
Thank you very much, Fernando. Anybody from the audience? Questions, comments?
I have a question. How many iterations do you use to get this course of beer?
Sorry, I didn't hear you.
How many iterations do you use to get that simulation and the course of beer?
This graph?
Yeah.
We applied, we basically did a sweep of values from 0 to 26 dBms. And for I think for the first 0 to 10 dBms, we did iterations of around 10,000 samples. But for the later cases, that went upwards of 100,000. They were very, very long simulations, but overall, I think it was within the standards that we expected. I don't know if I answered the question or.
Yeah. Well, yes, also I have a question.
Yeah.
Well, let me tell you that I am working in coding, channel coding. So I was a little bit sad that in your implementation, I didn't saw the block for coding. So
Oh, yeah.
my question is this, why in the implementation, you didn't include the block for channel coding?
We were basically trying to do a comparison between using this uh, tool, the 15 generator, as a means to access FPGAs, and we later on plan to work on VHDL exclusively so that we can kind of like do the comparison. Right now, that's basically what we're working on. Right now we're coding in basic VHDL so that we can do this comparison.
Okay, okay. Well, anybody else? Well, Fernando, thank you very much for your talk and
Yeah.
have a nice day.
Thank you.
The second talk would be transparent, circular, polarized quad-port MIMO antenna for 5G millimeter wave applications. The speaker would be Olukonda. Olukonda, good night over there. Are you ready?
Yes, sir. Yes, sir. I'm ready, sir.
Okay, so go ahead. You have 15 minutes.
Thank you, sir. Good afternoon, everyone. Today I'm going to present on transparent circular polarized quad port MIMO antenna for mmWave 5G applications. I am Golconda Satish, Department of EC, Andhra University of College of Engineering, Andhra Pradesh, India. Co-author Dwarapu Lakshmi Narayana, Department of EC, Vignans Institute of Engineering for Women's, Visakhapatnam, Andhra University, Andhra Pradesh, and India, from India. Contents: abstract, introduction, literature review, single port antenna, parametric analysis, design and analysis of MIMO antenna, diversity performance parameters of MIMO antenna, conclusion, references. Abstract: the polarized diversity parameters for port MIMO antenna is implemented on a PEXA glass, which resonates in the frequency range of 26.35 GHz to 29.39 GHz and 35.369 GHz to 41.03 GHz. Isolations among the antenna elements is more than 25 dB, achieved by using a star-shaped parasitic element placed in between radiators. The antenna exhibits right-hand circular polarization within the frequency range of 27.91 GHz to 28.71 GHz. The radiation efficiency and the peak gain of a proposed antenna is 84% and 6.57 dBi, respectively. Diversity parameters of a MIMO antenna is diversity gain is greater than 9.992 dB and ECC is less than 0.04. Torque is less than minus 15 dB. CCL is less than 0.015 dB bits per seconds per hertz, and the ratio of a meg is plus or minus 0.3 dB, which are within the acceptable range, and it can be used in 5G millimeter wave applications. Introduction. Wireless technologies are evolving rapidly, requires a compact and efficient antenna. MM frequency offers a high resolution, rapid data transfer, reduces interferences, and compact antenna size. Improve traffic management and security. The 28 and 38 GHz are promising for 5G systems. The combined with 5G technology, they enable data byte gigabyte data rate and enhances reliability. Problem statement suffers from high directivity and gain losses, air attenuation, and signal degradation. Motivation enhances performance, gain isolations, bandwidth, while maintaining compactness and achieving transparency. Literature review. These are the design priorities and transparent antenna designs. Single port antenna, where patch and full ground plane are using a AGH8, which is nothing but a silver tin oxide. This is a thin, transparent conductive material, and the substrate is used transparent substrate plexiglass. The single port antenna dimensions are 3 by 5 millimeter squares, and this table represents design dimensions in millimeters. Simulated reflection coefficients at different stages of a single port antenna. Where in the figure 2 we can see that first three antennas has resonating at a higher band. It is only showing a less impedance match. So after that, adding antenna 4 and antenna 5, we can see that in upper band it is resonating, its impedance match is increased, but in the lower band it is still it need to increase. By adding a inset feed method, proposed antenna resonates in dual band 5G millimeter wave applications. A dual band frequency ranges lower band 26.35 GHz to 29.39 GHz, upper band 34.69 GHz to 41.03 GHz. Resonating frequencies are 28 GHz and 38 GHz. Parametric analysis, where figure A shows inside feed length, where inside feed length is increases, where its impedance match is decreases at the upper band, but no change in lower band. After that, in the figure B, we can see by increasing the inside feed width, its impedance match is decreasing. In figure C, we can observe that outer circle width is increasing. The frequency are shifting towards right hand side, where dual bands are converting into single bands. We can observe at 0.25 and 0.30. And lastly, in figure D, we can observe that feed width, where feed width is decreasing, its resonating frequencies are moving towards left hand side. Design and analysis of a 4-port MIMO antenna. 12.5 by 12.5 millimeter square antenna, where 4 elements are placed orthogonally to each other, where in figure 5 we can observe that a star shaped parasitic element is added. Without isolation structure, the isolation among the antenna elements is 17 dB. After placing the parasitic element, isolation is improved by 10 dB as shown in the figure 7. Surface current distribution. From the surface current distribution, parasitic element plays a vital role that it will block the current to enter into nearby antenna. At 28 GHz, outer ring have higher amount of current, whereas at 38 GHz, inner circle have high amount of current. Therefore, proposed antenna is a frequency independent antenna. Total gain and radiation efficiency. The peak gain of an antenna is 6.57 dBi, and throughout the operating band, efficiency is more than 85% achieved. Right-hand circular polarization. The proposed antenna exhibits right-hand circular polarization during the band 27.91 GHz to 28.71 GHz. It can be visualized by using a E-field vector distribution for different phase angles like 0, 90, 180, and 270. E-field rotates in the circular fashion with respect to right-hand circular polarization. Diversity performance parameters of a MIMO antenna. Another correlation coefficient is determined the correlation between antenna elements. The acceptable value of a ECC must be less than 0.5. The diversity gain is achieved by receiving when its multiple versions of transmitted stream through different channel. Diversity gain provides improvement in multi-antenna system with respect to single antenna system. In practical application, DG value should be also close to 10 dB, where we can observe that in figure 11. Mean effective gain measures the antenna performance where the effect of environment is taken into the amount in the gain performance of the antenna. For equal power level, the ratio between meg should be plus or minus 0.3 dB. CCL is channel capacitive losses. Signal can be constantly transmitted over a channel, over a communication channel for a good MIMO performance. CCL should be less than 0.4 dB bits per seconds per hertz. Total active reflection coefficients is nothing but TARC. TARC can be defined as the return losses of a whole MIMO antenna array. Mathematically, TARC is the ratio of a square root of total reflected power divided by the square root of total incident power. Radiation pattern. From the radiation pattern of copolarization is more dominated than the cross polarization by 10 dB in figure 14 and 15 with the different frequencies 28 and 38. These are the comparison table of literature work with the proposed antenna. Conclusion. Designed a compact 4-element transparent MIMO antenna using AGH8 and plexiglass, achieved dual band operating at 28 and 38 with the bandwidth of 10.9% and 13.92%. Isolations improved to 25 greater than 25 dB using a parasitic element. A peak gain is 6.57 dBi and efficiency is greater than 85%. Parametric diversity parameters ECC, DG, MEG, CCL, TARC, meet 5G millimeter MIMO standards. These are the references I had been using. Thank you.
Well, thank you very much, Olukonda. Anybody from the audience? Questions? Well, I have a question for you. Your project is a 4-port MIMO antenna, right?
Yes, sir.
Yes, but you mentioned, I read somewhere in your slides that you mentioned that there are 6-port antennas also used. And in 5G, five-port antenna is the minimum they use in 5G. They used to have massive MIMO or 8-port antenna. The question is, this application you took for 4-port MIMO antenna is for a specific application, and why you didn't include, for instance, or how difficult it would be to make 8-port antenna with the same technology you used?
Sorry, sir, I can't listen your voice.
Well, let me take, if I take the microphone there, it'll be better? I guess there's some questions. Now you can listen? It's better?
Yes, sir. Yes, sir.
Yes. Okay, so the question is, if the 5-port antenna configuration you presented is for a specific application, and if we need, I don't know, 8-port antenna, it will be too much difficult to include it with the technology you used?
For going to 8-port antenna, it is difficult, sir, because of overcoming isolations, those all things, it is some kind of difficulty, sir.
Okay, okay. Okay. But anybody else? Well, thank you very much, Olukonda, for a nice talk.
Thank you, sir.
And next, our next talk will be shortwave radio audio signals denoising using a filter bank model with cochlear macromechanics. And Mario Jimenez will be our speaker. Yes. Cross. Here, 15 minutes. Thank you. Or a bit more. So, well, this is my presentation. I present this term, is a shortwave radio audio signal the noise is a filter back for the language cochlear Chinese. Please next. What, what is the problem statement about this topic? The shortwave signals to noise that is introduced by the atmosphere is considered an independent signal of similar to the wild and impulsive noise. This is interesting because if you have a system of radio, when the signal arrives to the atmospheric, it's introduced noise. This noise have specific characteristics. Is produced by the condition atmospheric on this part of the atmospheric. When the return the signal to the heart is contaminated with this noise. This is the sum, the result, the signal result is the sum of both signals. The original signal and the noise is present here. The next is what are the methodological classics of resolve these problems? Basically, is these two methodologies. The first is the filters or finite length impulse response, or the ear filter that is infinite length impulse response. In this part, there's several times the investigators use the linear phase filter design using Windows, the frequency sampling filter designs, the private linear phase filters, and this methodology is divided into principal topics: the analog low pass filter prototypes, including the Butterworth filter, Chebyshev filter, elliptic filter, and in the other is design with filters from analog filters that comprehend the impulse invariance and the linear transformations. There are there are another methodology that is very interesting because you have your signal in the time domain and your transformation to the frequency domain. You can eliminate the high components in the spectrum of the frequency domain and return and reconstruction the original signal. Next, please. In this work, I propose to use the response of the auditory system in the human. This interesting, this is a picture more shows a schematic for the ear. This part corresponds to the outer ear, and this part corresponds to the middle ear, and this part is the inner ear. The cochlea is here. This structure in the form of the snail is the cochlea. The cochlea inside is divided in three sections: the skull vestibuli, the skull tympani, and the skull media. This is the stapes. The stapes is a bone that conduces the mechanical energy to inside of the cochlea. Inside of the cochlea is full with a liquid similar to a water. But here in the skull media, the liquid is composed by sodium and potassium, and the difference of the pressure with the turtle along of the cochlea in the basilar membrane. The basilar membrane here in middle, this part is a cross section of the cochlea and represents how it is inside in the section. This part is the skull vestibuli, this is skull tympani, and this is the skull media. The basilar membrane is here. When a sound arrives to the system, the basilar membrane is exerted in a specific point. This specific places corresponds to a specific frequency that's excited to the systems. In the mark is present the organ of Corti. In the organ of Corti,
exists the outer eye cells. The outer cells is the element when the mechanical energy is converted to the electrical energy, and he arrives with the auditory nervous to the brain and is interpreted by the mind human. The next, please. Several words unimplanted filters bank. The classical works is here proposed by Davis and Merbenstein. This filter bank is applied to specific speech recognition in process of this topic. The filter or the interval frequencies of the filter is considered the Bell scales. The Bell scales is a relationship between the frequency and the perception of the musical tones in the auditory systems. But this completes all the response of the auditory systems, nor specific the inner ear of the cochlea. Other work that consider this methodology is proposed by Hersmansky. Hersmansky construction a filter band, but to the difference to this methodology is that this based in the Berg scale. The Berg scale corresponds to a frequency and the response of all the auditory system to the presence of the noise and in the sounds of the environment. Other work that is very interesting is proposed by Gitza. Gitza designed a filter bands that corresponds to the activate or desactivate the outer eye cells in the organ of corti. The next, please. Who is the cochlear macromechanics inside of the inner ear? This is a schematic of this element. This part corresponds to the oval window and the round window. The stage is here as the bone that introduces the mechanical energy inside of the cochlea. This part is the lycotrema. This element corresponds to the scale vestibuli and the scale tympani. They are connected in the apex with the lycotrema. The lycotrema is a hole that led to arrive the liquid in this part and to this part. The basilar membrane responds to a specific frequency that arrive to the systems and give this relation. This is schematic as percent the distance along of the cochlea and the displacement along of the basilar membrane. For example, the graph 1 corresponds to a specific frequency, and the 4 graphs correspond to other specific frequency. The classical model of these elements is in this form. The difference of pressure between the scale vestibuli and scale tympani are activated a part of the basilar membrane in similar form to the oscillator damping, and this equation is the result. This work was proposed for Lesser and Berkeley. Lesser and Berkeley in his work proposed this form or to give solution to this specific schematic in the cochlea. The next, please. Where this is validated with the work of Bekesi. Bekesi is the winner of Nobel Prize will present this relation. Here is the distance along of the basilar membrane, and this is the frequency. For example, you can see how the 100 cycles of hertz corresponds to a specific distance along of the cochlea, and for example, for 200 frequency cycles per seconds corresponds to this specific distance. Which is my propose. I propose to give solution to the model using the resonance analysis. I use this specific force. That this force corresponds to a sinusoidal of the frequency specific that arrive to the system, and the solution is a classical equation of the resonance analysis. It's a good, interesting question about what is the best value of the mass, stiffness, and damping that corresponds to the response of the basilar membrane along of the cochlea. The next. In the work of Nelly proposed these values and his variation along of the basilar membrane. He proposed in his work presents this graph when the distance from the states corresponding to the magnitude of admittance in the systems. I propose use the frequency of resonance in the solution of the relation, and this is the frequency of resonance. This frequency of resonance corresponds to a specific value of admittance, but these have the advantage that you can now the relation between the frequency and the distance along of the cochlea. This is my work, and in my work, this part corresponds to these frequencies, and this response corresponds to this frequency, and practically I have the same values that the work of Nelly with my methodology. The next, please. It's possible to know how is this relationship with these two equations. This corresponds the frequency to the distance along of the cochlea, and this corresponds the distance in relation to the frequency. It's possible to divide the basilar membrane in several intervals with equal distance along of the basilar membrane, and this specific place corresponds to a specific frequency. With these frequencies, it's possible to construction a triangular filter bank. This use the result intervals represent the behavior of the macro mechanics. The next, please. This is a filter bank that represents how the inner ear works. This part is the low frequencies, corresponds to this part around of the dicotrema. This part is the high frequencies correspond to this part around of the round window, oval window. This is the beginning of the cochlea, and this is the end of the cochlea. But I searched a question, very interesting. How is the best interval of frequency to construction the filter band? When I use the Spanish language for my tests and experiments, I use the specific frequency of the formals, that generation for the speech system. This corresponds to these frequencies, this interval frequency. In the low frequency is 80 hertz, and the high frequency is 1150 phase. The next, please. I present the results. I only use the vowel phonemes and the semi-vowel phonemes because the fricative and plosive sounds don't contain movement of the short vowels. For example, the fricative phonemes, the foco, tasa, the phoneme of if or t don't contain the movement of the short vowels. And for example, plosive, there's the plosive phonemes, for example, the phonemes p, pa, pato, or for example, the phoneme t, taco, don't contain, or in similar form, the fricative don't contain movement of the short words. For this specific condition, I only use the vowel and semi-vowel phonemes. This graph corresponds to a vowel A, where are not present noise here. And I apply the filters to the spectrum with the fast Fourier transforms that corresponds to this part of the samples. And when I apply the filters, this is the results. It's very interesting that the envelope of the signal is preserved. As you can see how the form of the signal is the same here. But it's very interesting that the high components in frequency for the specific noise that is here are not present here. Where I present the results where the ionospheric noise is applied to the original signal. Here, for example, this part corresponds to the ionospheric noise, and I apply the filter band. The filter band is here, and when I reconstruction the signal after the process of filtering, the signal is very good. The envelope is the same, but the components in high frequency are not present. This is interesting because in all the auditory system of the human, the formants is the most important elements of the signal for each resided in our systems. The next, please. I present here the results for the vowel O. In this part, I show the samples where are no present noise here. And I apply the filter bank, and this is the reconstruction of the signal of this spectrum. This is clearly that the envelope is the same, and this component in high frequency are not present here. But it's very clear that the form of the signal is the same. Where what's up in the presence of noise, the ionospheric here, this is the same vowel O, and this part corresponds to the noise of the ionospheric. When I apply my filter bank, with the reconstruction of the signal, is possible to see, and it's very clear that the envelope of the signal is the same, but the components in high frequency are not present. It's a very good result. The next, please. This is applied to a semi-vowel L. The semi-vowel use the movement of the short vowels, but are different to the vowels. For example, the phoneme L of lalo, or the phoneme im, for example, mama. These phonemes are semi-vowels. Are not specific phonemes, vowels, but they are considered semi-vowel because these phonemes use the movement of the charts here in the system of generation of the speech. This is the semi-vowel L. Is not present noise here. I apply the filter bank, and the reconstruction is very clear that the envelope of the original signal is preserved here. And now, when the semi-vowel L is with noise, you can see how all this noise is removed to the original signal, and the reconstruction is very clear that are not containing high frequencies of the spectrum. Here is very good. Please, the next. How can I validate that the principal performance of the Spanish language are preserved after the process of filter? I select the linear prediction analysis to develop these experiments. For example, I only apply the linear prediction to the signal with noise after the process of filtering only. This part corresponds to the first formant, and this is the second formant of the vowel A. And for example, you can see how the comportment of the results. This is the first formant, and this is the second formant, and the frequency is the same in the both results in the linear prediction. Here, for example, you can see what's up with the semi-vowel A. This part corresponds to the first formant, and this is the second formant. And the values of the frequency in this part and in this part is the same. It's the same value of the frequency. Next, please. I present signal to noise radio applied to this is the words that I propose. This is very interesting because in the three case, the signal to noise radio is positive. Are not negative in our experiments. This is positive, and it's clearly that the value is the result is very good. For example, for the vowel I or for the vowel O, it's clearly the signal noise relation is very well. In the phoneme L, so it's good the results. But the important is that the value is positive. Yes, I present so the results of intelligence. I consider only 16 adults with a range, age of range between 19 and 24 years, of which 22 were women and 38 men. It is considered that none of the people have suffered any hearing impairment of the site related to hearing disorders. It's very interesting, the results, because with the noise signal is present to the people, it's very poor the results. And with the noisy signals is present to the people, it's very well. The You can see in the previous graph, the best result is present and corresponding to this result in the intelligence test. The next, please. What is the conclusion of these words? The filter bank classical designed using the general response of the auditory system. For example, the words of Hermansky, of the words of Gitza, or the classical words of Davis and Bernstein that is used to specific speech recognition systems. However, the filter bank developed considers the distance frequency relation in the basilar membrane obtained from the Crocker macromechanics, that is my course. The filter bank is efficient for the sample frequency. I proved with two frequency samples. The first is 44 kilohertz and 16 kilohertz. This is because I save my samples in a file wave. This is the standard frequency of the 5 watt. I work in this format of the audio, and I select the interval and corresponds to the frequency low of 80 hertz and the high frequency of 100, so 1150 hertz. Another conclusion is the preservation of the formats of the Spanish language. It's possible to see in the graph how the frequencies are the same after the process of linear prediction in the experiments. This is the most advances of this work. I declared that the phonemes, fricatives, and plosives are not present in the test because they don't change or generate movement in the short vowels or in the generation of speech systems. The tests on the intelligent were performed and obtained after filtering good results in the three cases of the semi-vowel. The next, please. This is the basic bibliography. This is the classic work of Davis and Bernstein. This is the classic works of Hermansky. This is the work of Itza. This is a book about the mathematical physiology of the inner ear. This is a good reference. This book described all the macromechanics in the cochlea and proposed several solutions, for example, Fourier series, and for example, the damping harmonic oscillator, the difference of pressure, the fluid mechanics here. And this is my work when I present the distance frequency relation in two-dimensional model of the cochlea. When my relation, I construction these filters, and with these filters, I propose to selecting the interval frequency of the format of Spanish language to filter in the noise of the hemispheres. The next piece. The next piece. Thank you very much. If you have any questions, please.
People from the audience, some question? Oh, very good. Yes. I have a question. You mentioned that you try to select the best vowels or phonics to get your data, but these vowels were recorded by you in a laboratory, in an electronic to find them in a database.
I use a system of radio in short. I have a radio, shortwave radios, and my radio can lead to recording the samples that I hear in the radio, and I can select the frequency sampling, the beats, if one signal chain or two or monophonic or stereophonic. I can select it in my radio, and I recording samples, and I use my samples experiments in MATLAB.
Okay. According to your methodology, did you find any coloration due to the way you record your samples? Because
No, the original samples.
yeah, but you know that most of the recording devices have a special color, but they have not a linear response.
No, the original samples. The original samples. For example, in speech recognition, you use parentheses. Parentheses is clearly the process after every system in speech recognition. I don't use parentheses. For example, I don't use a filter after the process. No, I use specific samples with my radio. Give me the samples.
Then your radio has a linear response, a linear curve. If I have a audible spectra from the
the sampling frequency is 44 says corresponds to this characteristic. Yes.
Okay.
Well, now hearing these questions, it came something to my mind. For these vowels, what was the period of time you analyzed? Because it's not the same when you study the vowel.
It's very interesting.
Or do you
It's
just
very interesting question.
So there is something different because even when you're speaking, you don't say ma.
Yes,
you
yes.
say,
Okay.
ma.
It's a very interesting question. When I relate process of speech recognition or speech synthesis, you select windows of 20 milliseconds or 15 milliseconds, because this interval corresponds to the minimal transitions between the phonemes. When you speak, the phonemes are continuous. It's a big problem in the process of recognition because in the word, for example, mama, if you can hear the phoneme of M and the other phoneme is N, with the connection between the two phonemes is the minimal interval is 20 milliseconds, 20 or 50 milliseconds. And this is the minimal size of the window that used for relation the every analysis of speech recognition or synthesis recognition.
And when you have combinations, for instance, you say even the word, you say mama, but when you say mami, you have even the vowel A and the vowel
Yes.
I.
Yes.
And if the transition is rather fast, so you will have some transients for the filter between ma and mi, ma, mi. So how, or does this have an impact? on the
Okay.
accuracy?
But you pronounce different words. The phoneme is similar in this part, not in the transition. In the transition, it's very different. If you pronounce, for example, mama, pata, the A is the same, but the transition is different. Would you have the transition between the phoneme of P and A, or for example, in the end of A, mama, pata, the transition is different. But here, what you pronounce only the phoneme is the same. Phoneme is the same. The transition is not the same. Okay. But what you pronounce the form for the Spanish language, the English language, the German language is the form of that the language works in these idioms. For example, in the Chinese and the Japanese, is all no, Japanese is similar to the in the European language. But for example, the tonal language is different. For example, the Otomi here, Mesoamerican language is very different because these languages are tonal. But when you pronounce the same vowel, for example, is different to interpretation for this language, for this specific language.
Okay, thank you very much for the interesting talk. Anybody else question?
Yes, please.
Can you go to slide 11?
Excuse me?
Can you go to the slide number 11?
11.
11?
Yeah.
Yeah, 11, it's okay.
Okay. How did you establish the noise floor to have this ponderation in the amplitude in dBs?
It normally says.
Yeah,
It
but
normally says to 1.
I see that.
Yes, the amplitude is normally says to 1. Yes, This is in 16 bits.
Yeah, but after the
Yeah.
two. Fast Fourier transform.
No, when I reconstruction, the signal, when I remove this part of the spectrum, and I reconstruction the signal, the result is normalized to 1.
Because I can see clearly and I see like 100.
No. You can see 1 and minus 1.
In the
One minus one.
side.
Yes, this is with the object to compare it to in similar conditions, both signals.
Then you made your report and also you had an decibel meter and you applied the normalization.
No. I use the maximum value. The maximum value is here. Maximum value is here.
Yeah, that is the
I divided all the vector between the maximal value and the same. I found the maximum value and I divided the vector, all the vector in
and the
between.
graphs that are at the right, can you tell me which is the lowest and the highest? Because I can see clearly.
No, but this is the time domain. This is the time domain and this is the frequency domain.
Yeah, but in your amplitude, it goes from 0 to where? Because I can see clearly.
And this is zero.
No, in the other, in the
The right.
The order here, no, it's the result of the fast Fourier transform.
Because go to the next slide. In the next slide, you have also next, please. Next,
That's
another one that one is also a fast Fourier transform.
linear prediction. This is linear prediction.
Because when I apply the fast Fourier transform in MATLAB, I have some.
I don't use the function of MATLAB.
Okay.
I program my own function.
But
My own function. No, I don't use the function. I only use MATLAB to graphs, to present the graph. I don't use the function of MATLAB. I programming my own function of fast Fourier transform. I don't use
okay, but the main of this question is how does your function adjust the amplitude in the frequency domain?
the amplitude in the frequency domain.
Yeah, because in your samples they are normalized, but when you apply the fast Fourier transform, the amplitude is not.
But I'm only interested in the frequency.
Okay.
I don't interested in the amplitude because the formats are frequency. Don't have.
Thank you.
Thank you very much. So that will be all for today. Thank you everybody for your assistance.